So now that we've talked about moments in scalar form and in vector form and how to find the moment axis, now I want to see how can we calculate a moment about a specified axis. So we might think of this as something like we have a tire. This is the tire on your car, right? And you want to tighten in one of the nuts here, right? Right, tighten that on your car. And so we've got this wrench coming off of it, but our moment axis might not be in line with this wrench here, right? It might be, the moment axis might be off some way like this, and maybe we want to find out, well, what is the moment about this axis directly coming perpendicular off of that nut, right? How do we find what this moment is? If this is the moment about the origin, given some force pushing down on this bar rotating the nut. So this is where we might want to find it about a specified axis. We can kind of think of it as like a component of a moment, but we always describe it in this way as a moment about a specified axis. So it gives you the axis that we're interested in, and we're going to find the moment about that axis. And there are 4 steps that we go through to do this. So first is we're going to put every component into Cartesian form, right? So we need to make sure that our force is in Cartesian form, our R, our position vector, is in Cartesian form, and then also a unit vector describing the axis, right? We need some way to describe the axis that we're interested in, so we find a unit vector describing that axis. Then, right, so that's step 1, all of those in Cartesian form. Step 2 is going to be finding the moment about any point on the axis. So usually we'll take this about the origin, that's usually the easiest way to do it. But we'll take just the moment using our standard cross product, R cross F. Now this has to be on the axis of interest. This is the most critical point. It has to be on the axis of interest, the point that we take our initial moment about. But usually it's the origin. However, we can select any point that we want, as long as it's on that axis. Step 3, to find the moment about the axis, is we're going to take the unit vector of that axis and take the dot product of this unit vector with this moment equation that we just found. So the moment about the origin, or R cross F. And this gives us a magnitude, right? A dot product always gives us a magnitude. So we do the cross product first, then the dot product, and that gives us the magnitude of the moment about the axis, which is sometimes sufficient for an answer. We might be able to stop there if it just asks for a magnitude. If it asks for the vector form of the moment, what we'll have to do is take this moment about the axis and turn it into a vector by multiplying that magnitude by the unit vector of the axis. So these are the 4 main steps, and we can sometimes shortcut this. So I'll give you this shortcut equation here. Of course, we'll always have to put them in Cartesian form. I'm going to keep that there. But steps 2 and 3 can be combined into this handy dandy, I'll write this a little bit bigger, the moment about the axis is going to be that unit vector about the axis dotted with R cross F. We can rewrite this as the x component of the unit vector, the y component of the unit vector, and the z component of the unit vector, replacing I, j, and k in our cross product. And then you have the position components and the force components. Right, so this is just our cross product equation, but instead of I, j, k, we can put in the components of the unit vector to kind of skip that step, right? To make this all one combined thing. This is a dot, sorry. And this will give you the magnitude of the moment about the axis. So we can use this shortcut equation as well. Let's take a look at a couple of examples. It'll make a little more sense as we work through the steps together. Okay, so in this example, I have a lever that's in the ZY plane, and a force coming off of that lever that has the alpha, beta, and gamma angle components, giving me the direction in space that that vector is going. And then I also have where the lever is located in space, right? So I have a force coming off of this, and I have my distances and some things so I can put this into Cartesian form, right? First thing that we're going to do is put everything into Cartesian form, right? Here we're determining the moment about the x-axis. So let's look at that first. About the x-axis, this means that our unit vector for our axis, if we're going along the x-axis, it's only going to be 1 I hat, right? That's representative. That's the unit vector for the x-axis. So our unit vector for the axis of interest is going to be 1 I hat. Or you can just write I hat. The 1 will be implied. We're also going to need our force vector and a position vector in Cartesian form. So our force vector, we're going to get using our cosine alpha, beta, gamma equations. So that's our x component is 200 times cosine alpha. This x distance here is this 120. 200 cosine 120. I hat. That's an I. I hat. Plus our y component here is 60 degrees, so plus 200 cosine 60 j hat. That's our y component. And then our z component coming off the x-axis is plus 200 cosine 45 j hat. So that's our force vector broken down into its Cartesian form. Not j hat, k hat, sorry. Z direction, k hat, right? 200 cosine 120 I hat plus 200 cosine 60 j hat plus 200 times cosine 45 k hat. K hat, z component. So that's our force vector. But the last one we need is a position vector. And I want to note that it doesn't really matter where your position vector comes from, as long as it is attaching somewhere on your axis of interest to somewhere on the force's line of action. Right, so you'll recall the force line of action is the line that the force goes through. Right? Even if the force doesn't appear to be that long, this is the line of action. This is its axis, essentially. So anywhere from the axis of interest to anywhere on the line of action of the force is where we can build a position vector. For me, I'm going to go from the origin because it's usually just the easiest place to find a position vector. And I'm going to just build my position vector from the origin to F. Because I have those distances already, right? It gives me in the ZY plane the 0.3 meters and the 0.25 meters in the Y and Z direction. Since they already give me those, it's going to be the easiest place, right? The origin here is on my x-axis, and I'm just going to connect it to the force vector. So this green vector here, this is my R vector. And I have those distances, so I can say my R vector is in the Y direction, 0.3 j hat, right? And then up in the Z direction, plus 0.25 k hat, right, in the Z direction. These are given in meters, this was given in newtons, and then the unit vector has no units, right, because it is a unit vector. It represents a unit of 1 with no dimensions attached to it. Perfect, so that's the first step. We have that down. Now we need to actually just find the moment. So step 2 is finding the moment of R cross F. So in this case, we're going to have our I hat, J hat, K hat, then our then our R vector, 0, 0.3, 0.25, and then our force vector, which if I multiply out these, I put these 200 cosine 120 into my calculator, I'm going to get negative 100, then a positive 100 for the J hat, and 141.42 for my K hat term. And then I'll just multiply out the matrix as we had done before, right? We've done problems like this before. We take I hat times 0.3 times 141.42 minus 100 times 0.25. That's the I hat component. Minus J hat component, always minus J hat component, of 0 minus negative 100 times 0.25 plus the K hat component of 0 minus negative 100 times 0.3. And this gives us a vector answer, right? Our moment is going to be in a vector answer. So let me simplify that down. I'm going to plug all those into my calculator so that I get the moment. This is the moment vector about the origin, right? About the origin. It's going to be 42.43 I hat minus 25 J hat plus 30 K hat. So that's the moment about the origin. That was my step 2. Now my step 3 is to do the dot product, right, to get the moment about the axis. This is about the x-axis. I do the dot product of my unit about the axis with that moment that I just found, that R cross F. So here, it's going to be, we said our unit vector was I hat. So I hat dotted with this whole vector here. I'm gonna just, I'm gonna move him down. Right, here's my vector. Taking the dot product of I hat with this guy. So when we do that dot product, since there's only an I hat term, these other two terms are going to go to 0, right? Because you're going to have I hat times I hat plus J hat times J hat plus K hat times K hat. And since there's no J hat or K hat terms, these guys are going to go to 0. And what you're going to end up with is the moment about the axis. The magnitude of the moment about the axis is 42.43 Newton meters. So that would be the magnitude. That's the magnitude of the moment about the axis. If I wanted to get the moment vector, I would multiply this moment about the axis, this magnitude, times the unit vector. So I get m axis times the unit vector of the axis, which in this case is going to be the 42.43 times I hat, right? Just one single I hat. So I get 42.43 I hat Newton meters. And that's my moment about the x-axis. Now, our problem didn't actually state when it said determine the moment, it didn't state whether it wanted the magnitude or the moment vector. So either one of these answers would be fine. And we see that they're basically the same, right? It's either 42.43 Newton meters, or we actually give it a direction and say that, okay, that's entirely in the x direction because this is the x-axis, right? Since it's just along one of our main unit axes, it's going to have the exact same magnitude. But this may not always be the case. We may not be interested in just the x-axis or just the y-axis. It could be about some other line that we're interested in. So let's look at an example like that. So in this example, I'm wanting to find the magnitude of the moment created about the line AB. And the big issue that we notice about this is that our line AB doesn't actually go through the origin here, right? So we're going to have to find some different points to define a position vector. So we're going to do our first step first, which is in Cartesian form, do our force vector, our unit vector, and our position vector. So I'm going to do the force one first because that's going to be the easiest one, right? It's just like we've been doing this whole time with resultant forces and everything. We can see we've got a nice little 3, 4, 5 triangle here, right? This side is 3, this side is 4, and so we know our hypotenuse is 5. So when I make my force vector, it's going to be entirely in the zy plane, right? This is entirely in the zy plane. So it's going to be this 4/5, right? 4 is the y component, 4/5 times 650 for the y component, j hat. And that is in the positive y direction. And then minus, since it's in the negative z direction, minus 3/5 times 650 in the k hat direction. So I can simplify this, right? I can just write our force vector simplified is 520 j hat minus 390 k hat. So 1 down, 2 to go. I'll do my unit vector next. Let's go ahead and define the unit vector that makes up line AB, right? It's not as simple as just our x-axis, which is just 1 in the I hat direction. Now I'm going to have to go back to what we learned with position vectors and how do we make a unit vector, right? It's that position vector AB over the magnitude of that position vector AB. Right, so if I find my position vector AB, I'm going to see that I have from A to B, I'm going in the negative x direction by 2.5 feet. And then in the positive y direction by 6 feet. So that's my position vector, right? No z component. I'm not even going to bother to write it, right? I can go ahead and put in here 0. But it's perfectly fine for me to just write it with 2 units, with just the xy, because it's in the xy plane. And then, of course, to get the magnitude, I take the square root of the squares. So 2.5 squared plus 6 squared plus 0 squared. And I'm going to get a unit vector when I plug that into my calculator of negative 0.3846 I hat, right, x component, plus 0.9231 j hat. That's our y component, and there's no z component. So this is our unit vector that defines the axis. And finally, we have to pick a position vector. Now remember, it can be anywhere that connects the line of action of the force to our axis of interest. So I'm going to pick what I see is the easiest position vector, the least complicated position vector, which to me is connecting this point B 2 feet over to where this line of action of the force is hitting the y-axis. So this vector, this position vector, R, is negative 2 j hat. And remember, we could have picked wherever, you know, I could have gone from A to this point Z up here, but then I would have had two components instead of having just this one single Y component. I could have gone anywhere along this line to this line, right? But to me, just going -2 in the j hat direction gave me the least components, gave me the least amount of math I had to do. It was the most obvious choice that I saw. But again, your answers will all come out in the wash, right? Everything is going to work out no matter what position vector you choose for these cross products, for these moment about an axis, because we have that unit vector that's washing everything out, basically. It's clarifying everything so that it doesn't matter what the position vector we actually picked was, as long as it connects the two lines. All right, so I have all of my components now, so I'm just going to plug them in to that shortcut equation that we found. I'm going to get all these out of my way. Oops. So I had this, the moment about the AB axis was the unit vector AB dot product with R cross F, right? And it just needs a magnitude. So we don't need to go back and find an actual vector for this. It's just wanting a magnitude, which is what this equation gives us. And we said the shortcut for this was the unit vector on top, then the position vector, then the force vector. So our unit vector was -0.3846 in the x component, positive 0.923 in the y component, and then no z component. That was our unit vector. Then our position vector, right, we said was -2 j hat, so that's 0, -2, 0. And then finally the force vector that we found. 0, 520 for the y component, and -390 for the z component. And then I do this cross product exactly like I would do our cross products beforehand, just instead of I, j, k, now we actually have numbers in the top row. Right, so we're going to have -0.3846 times -2 times -390 minus 520 times 0. That's 0. Minus our j hat component, so minus 0.923 times 0 times -390 is 0, minus 0 times 0 is 0. So this component will go to 0. And then plus our k hat component here was 0, so everything in that term will go to 0 as well. And we're left with, if I multiply this out, this -0.3846 times -2 times -390, I get -300. -300 pound-feet. Pound-feet. And that's it. That's the magnitude of my moment about that line AB. Okay, this is going to be our final example, but I'd like you to try to work it on your own before we talk about it together. It gives us our position vector, and I have the angles alpha, beta, gamma listed here. Alpha is 60 degrees, beta is 60 degrees, and then gamma is 45 degrees. And it gives us our position vector and our unit vector locations, right? Our unit vector is along this axis AA, and then our position vector is showing this line from axis AA to our force vector F. So go ahead and give it a try, see how far you can get, and then we're going to talk about it and walk through it together. Okay, so our first step is to break everything up into Cartesian form, put all of our vectors into Cartesian form, right? We see the three that are listed here. We're going to go ahead and break them down. I'm going to do the force vector first, just because I think that's the easiest one, right? So I have my 30 newtons. I'm going to do 30 times my cosine alpha, that gives me my x component, 30 cosine 60 I hat, plus 30 cosine 60 j hat, right? That's my beta, that's my y component, plus 30 cosine 45 gives my z component, my j hat there, right? Easy enough. Back from a few weeks ago, we should be comfortable with using these alpha, beta, gamma breakdowns into Cartesian form. We've got our force broken down. Now we'll look at what our position vector is. So it gives us here, and it calls it ROA, right? R from the origin O, which is sitting on axis AA, to point A, which is where our force vector is starting. So if we look at this, our vector, we're going up, which is the z direction, by 150 millimeters, right? 150 millimeters in the z direction. Millimeters, right? In the k hat direction. And then we're going backwards, right? Backwards in the x direction by 100 millimeters. So that's a negative 100 I hat. Now, we have a choice we can make here, right? We can decide whether we want to convert these millimeters into meters, or if we're just going to leave them as millimeters. The only thing that it's going to change in our answer is whether our final moment answer is Newton millimeters or is in Newton meters. For now, I'll leave it in millimeters just to show you how the math would work out that way. And then we can talk about converting it into Newton meters if we wanted to. So here's our position vector, right? Minus 100 I hat plus 150 k hat. And then our unit vector. Our unit vector for the axis AA. Now notice axis AA is actually exactly parallel to the y-axis, which means that it has the same directional unit vector as the y-axis, and that is just j hat. Just one single j hat. It follows the y-axis exactly. It's just offset, right? It's offset by that position vector of that, 150 and 100 millimeters, but it's exactly parallel to the y-axis and will follow the same unit vector. Our unit vector is just j hat. Now that we have all these, we can plug them in to our handy-dandy moment magnitude equation, right? Our unit vector, AA, dotted with R cross F. So let's go ahead and plug those in. Move these guys out of the way. So we get, again, our shortcut form is going to be the unit vector first. So we said it was j hat, so 0, 1, 0. Then our position vector was negative 100, 0, 150. And then our force vector, if I multiply out that 13 cosine 60, or 30 cosine 60, I get 15, 15, and then the last one was 30 cosine 45. That gives me 21.2. So I do my cross product here. I get 0 times a bunch of stuff, doesn't matter, just 0 makes that 0. Minus 1, right, always minus the j hat term. 1 times negative 100 times 21.2 minus 15 times 150. And then the k hat term again is 0, so that'll be plus 0. So we end up with a magnitude for our moment about axis AA of 4,370 newtons times millimeters. Newton millimeters, right? Because we didn't convert them out of millimeters. So this is the magnitude, but it did ask for the moment in Cartesian vector form. So to do that, I take this moment magnitude, AA, and multiply it by the unit vector of AA, which we said was just j hat, so we're going to end up with 4,370 j hat Newton millimeters. And of course, if we did convert this to meters before we did our position vector, we could convert it at any point. So we could convert it in our position vector, or we could convert it now if we wanted to, just by dividing by 1,000, right? And we get 4.370 j hat Newton meters. So either one of these answers would be 100% acceptable, right? Just depends on what units you're using, what units you're working in. If you care about it in millimeters or in meters, whatever the question is asking you for, or if it doesn't ask, whatever you're just more comfortable.